Yes, right. So, welcome you all for today's EMF session. A very good morning to you all. In my last class, I have discussed about Gauss law and its applications. In before we apply Gauss law to determine electric field, we need to assume an imaginary surface, and that imaginary surface is nothing but Gaussian surface. And we have discussed what type of Gaussian surface we can assume for different charge distributions that we have discussed, right? For example, for a point charge, spherical surface is assumed as Gaussian surface, and for a spherical charge, spherical surface is assumed. For a line charge and surface charge, a cylindrical surface is assumed as a Gaussian surface, right? And we have seen electric field due to a point charge using Gauss law. We have seen, right? So a point charge, a positive charge is located at the origin, right? And a Gaussian surface, right? A Gaussian surface is assumed, which is a sphere. A spherical Gaussian surface is assumed. And from Gauss law, we know that psi is equal to Q, right? And Q enclosed, right? Charge enclosed on the Gaussian surface. And psi is equal to surface integral d dot ds, and q is equal to q enclosed for point charge, right? And as we know that there are two conditions to be satisfied in order to use Gauss law. One is charge should be uniform on the Gaussian surface, and second one is field, electric field should be normal to the surface, right? So therefore, if field is uniform, then d can be taken outside the integration, and we have this d into area, right? Area of the Gaussian sphere, 4 pi r square, right? And from equation 1, psi is equal to q, right? So equating those two and simplifying, you will get this equation, right? So this is nothing but electric field due to a point charge. In a similar way, we have also, right? We have also discussed electric field due to a line charge, right? A line charge is considered along z-axis, right? A line charge is considered along z-axis, and a cylindrical Gaussian surface is assumed, right? So this is a Gaussian surface. Right? So this is a Gaussian surface. Cylindrical Gaussian surface is assumed, and the radius of the cylinder is rho. Right? So therefore, from Gauss law, Q enclosed, right? Q enclosed for line charge, line integral rho L dl, and for uniform charge, rho L can be taken outside. Line integral dl is L, length of the cylinder. Right? So therefore, rho L into L, and similarly, xi is equal to surface integral d dot ds. D can be taken outside, and area of the cylinder is 2 pi rho into L. So equating equation 2 and 3, we have this one, right? And in fact, this equation we can write in like this, right? Xi is equal to integral d dot ds top plus surface integral d dot ds bottom plus integral d dot ds sides, right? So actually we have to write like this because cylinder, right? So cylindrical surface consists of different planes, right? So top, so this is the top one, right? Top plane, and this one is bottom, right? Bottom and sides, right? So these are the sides, right? So therefore, um, integral d dot ds with respect to top is 0, right? Integral d dot ds with respect to top is 0, and integral ds with respect to bottom is also 0, right? Bottom is also 0, right? Why? Because as we know that here, and this is the line charge, right? uh, and a cylinder is assumed, cylindrical Gaussian surface is assumed, right? So this is top, and this one is bottom, right? And these are sides, right? And this is line charge, right? So this is the line charge considered. And as we know that the electric field due to line charge is normal, like this, right? Electric field is normal to the line charge, always directs like this, right? And this direction also, right? In this direction, everywhere normal to the line charge, right? Everywhere not everywhere normal to the line charge, right? Like this, right? So therefore, and this electric field and these flux lines, we can say it as flux lines. So these lines are parallel to top, here top. So these lines, the direction of electric field lines, and this is parallel to top, right? Top surface, right? Parallel to top surface. And similarly, and these lines, right? These lines on bottom also parallel to the bottom, right? Parallel to the bottom, right? So therefore, electric field top and bottom is 0, right? Top and bottom is 0. But whereas to the sides, so this is side of a cylinder, and this is the electric field flowing in this direction. So therefore, they are perpendicular. So electric field is perpendicular to sides, right? Got my point? Electric field is perpendicular to the sides. Electric field is perpendicular to the side. So therefore, integral sides is having non-zero, right? Is having non-zero, right? So therefore, integral d dot ds is nothing but this one, right? So this you will get this one, integral d dot ds sides, you will get this one, d into 2 pi rho l, this you will get, right? So this is our and equating equation 2 and 3, equating these two and simplifying for electric field, you will get this expression. So this is nothing but electric field due to a line charge, right? So this is how we can determine electric field using Gauss law, right? And now uh, let us apply Gauss law in order to find the Gauss law and surface, right? Gauss law and surface charge, right? So that means surface charge, electric field due to surface charge using Gauss law, right? Electric field due to surface charge using Gauss law, right? Electric field due to surface charge using Gauss law, right? So let us assume a surface. Here I will assume a disk charge, right? Disk charge. As I have said earlier, disk charge or plane charge or surface charge are same, right? All are same, right? So therefore, let us assume a disk charge, right? So this is a disk, right? Disk in the sense it is a circle, right? So a CD, right? CD type, right? So disk charge, and charge density on the surface is rho s, right? Charge density on the surface is rho s, right? So therefore, in order to determine electric field using Gauss law, we need to assume a Gaussian surface, right? We need to assume a Gaussian surface. What type of Gaussian surface we can assume here? We can assume a cylindrical, right? A cylindrical Gaussian surface, right? So assuming a cylindrical Gaussian surface, right? Assume a cylindrical Gaussian surface that occupies a differential area, that occupies a differential area ds, right? So let us assume a cylindrical surface like this, right? And right, a cylindrical, right? A cylindrical Gaussian surface I have it. Cylindrical Gaussian surface I have assumed, right? That occupies a differential area ds, right? This one. So this is a differential area ds. This one. So this is the differential area ds, right? So this is the differential area ds, and similarly this is also same ds, same area, right? So this is ds occupying a differential area ds, right? Occupying a differential area ds, right? So the direction of electric field is this one. So this is the direction of electric field density, in other words, right? So this is electric field density, right? So let us apply Gauss law to determine electric field. So what is Gauss law? Xi is equal to Q enclosed, right? Xi is equal to Q enclosed, where xi is equal to surface integral d dot ds, right? Xi is equal to surface integral d dot ds, right? Um, and um, um, and Q enclosed is equal to surface integral rho s ds, right? Q enclosed is equal to surface integral rho s ds, right? So these are the two equations, and let us say this is equation 2 and this is equation 3, right? So now uh, from equation 2, xi is equal to integral, we have assumed a cylindrical surface, a cylindrical Gaussian surface. So therefore, cylindrical Gaussian surface in the sense top ds plus bottom ds plus sides, ds, right? And here, as we know that the here I will draw this separately so that it will be clear to you. Right? So this is the disk charge, and we are assuming a cylindrical surface, right? We are assuming a cylindrical surface, and as we know that the electric field due to any surface is normal, right? With respect to line or with respect to surface, the electric field is normal to the surface. So normal to the surface in sense what? It directs like this, like this. So this is the direction of electric field, right? This is the direction of, even for downwards also, this is the direction of electric field, right? So this is the direction of electric field, right? Electric field E bar or D bar, density, flux density, D bar, right? So therefore, in this case, this electric field is normal to top, right? Electric field is normal to top surface, and similarly is normal to bottom surface, right? Electric field is normal to bottom surface, and whereas the electric field is parallel to sides. So this is side, and the direction of electric field is parallel, right? Parallel to sides, right? So parallel to sides, right? So therefore, with respect to sides is 0, right? With respect to sides is 0. Integral d dot ds with respect to sides is 0, right? So electric field with respect to sides is 0. So therefore, we have top and bottom, right? Top and bottom, right? So let us say on top, this one is dn, right? dn normal to the surface, and this is also dn normal to the surface, right? And this will become, right? So this will become, as we know that field is uniform, right? So field is uniform, so this is equal to dn bar top ds plus dn bar bottom ds, right? So this is nothing but, what is this? So this is nothing but area, right? Area. So this is nothing but area, and this is nothing but area, right? So so what is area here? Area is ds, right? Area occupied. So area occupied is ds, right? So therefore, we can write, right? We can write it as this is equal to dn bar, and let us say here ds, you may get confusion, right? So therefore, let us say the area is delta s here. This one area is delta s, right? Area, this one, this area. So instead of ds, right? Instead of ds, let us say delta s, right? So therefore, this will become dn bar delta s plus dn bar delta s, right? So this is the field with respect to top and the field with respect to bottom, right? So this is equal to 2 dn bar delta s, right? 2 dn bar delta, and let us say this is equation 4, right? Now similarly, from equation 3. So what is equation 3? So this is equation 3, this one. So this is equation 3, right? This Q enclosed, right? Equation 3. Taking that equation, we have, so from equation 3, Q enclosed is equal to surface integral rho s ds, and this is equal to rho s surface integral ds, right? So uniform, charge is uniform, therefore rho s can be taken outside, and this is equal to rho s delta s, right? Because this is nothing but area, right? Area delta s, right? So here, let us say this is equation 5, right? This is equation 5, right? So therefore, equating equation 4 and 5, right? We know that the gas law xi is equal to Q enclosed. So therefore, equating, right? Equating equation 4 and 5, right? Equating 4 and 5, we will get 2 dn bar delta s is equal to rho s delta s, right? Therefore, delta s here, and we have dn bar is equal to rho s by 2, or this can be written as d bar is equal to rho s by 2 an bar, right? Because normal unit vector an bar, right? And from this we can write e bar is equal to rho s by 2 epsilon naught an bar, since d bar is equal to epsilon naught e bar, right? So this is how we can determine electric field due to a surface charge using Gauss law, right? Using Gauss law, right? It's very simple, right? So using Gauss law, determining electric field is very simple, right? So therefore we have, with this we have completed Gauss law, right? So overall, we have discussed two concepts so far, right? Two concepts so far. Number one, Coulomb's law, and number two, Gauss law. Only these two we have discussed so far, right? So using Coulomb's law, we have determined electric field due to point charge, electric field due to line charge, and electric field due to surface charge, right? So by using Gauss law also, we have done the same expressions, right? So equations are the same, but different approaches: electric field due to line charge, and electric field due to surface charge, right? And we have derived those expressions, right? Electric field due to point charge is equal to q by 4 pi epsilon naught r square ar bar, and this is equal to rho l by 2 pi epsilon naught rho aero bar, and this is equal to rho s by 2 epsilon naught an bar, right? So these are the three expressions we have discussed so far, and the problems related to these three we have discussed so far. That's it, right? So remember, only two concepts we have discussed so far, right? Coulomb's law and Gauss law, right? So Coulomb's law and Gauss law are for the same purpose, right? What is that purpose? Determining electric field. Determining electric field due to point charge, determining electric field due to line charge, and determining electric field due to surface charge, right? And problems related to those two that we have done so far. That's very simple, right? So only that we have discussed so far, right? And now we are going to enter into the third part, right? So first part is Coulomb's law, second part is Gauss law, and third part, right? So third part, another concept we are going to discuss here, right? And that is mm, electric potential. Electric potential, right? So um, electric potential, and this is the third concept, right? So first one is Coulomb's law, second one is Gauss law, and third one is electric potential, right? And electric potential is also to determine electric field, right? Is also to determine electric field, right? So and determine electric field due to point charge, line charge, and surface charge. And this is the third approach to determine electric field, right? So here, before we enter into electric potential, we need to understand what is energy expanded in moving a positive charge in the presence of electric field, right? Energy expanded in moving a positive charge in the presence of electric field, right? So this we need to understand, right? So let us say a positive charge, a positive charge Q in the presence of electric field, in the presence of electric field E bar, right? A positive charge Q in the presence of electric field E bar is moved a distance dl bar, or dl is moved a distance dl, right? Is moved a distance dl, right? So then force exerted by the electric field is given by, right? So please try to understand, a positive charge Q in the presence of electric field E is moved a distance dl, then the force exerted by the electric field, as we know that earlier we have discussed, right? So let us say this is a point charge Q, right? If a test charge, right, if a test charge Qt is moved around, right, is moved around a known positive charge, then we can say that a force, right, a force exerted on the test charge, right, a force exerted on the test charge everywhere, right? A force will be exerted on the test charge everywhere due to the electric field, right? Due to the electric field, right? And that force, right? That force is equal to F is equal to QE, right? In other words, let us say F is equal to QE, right? F is equal to QE. So this is the force exerted by the electric field, right? This is the force exerted by the electric field, right? If you want to move a test charge, right? If you want to move a test charge in the presence of electric field, what is the force we need to apply? Already a force is there because of the electric field, and that force is F is equal to QE. And if you want to move a test charge QT, right? If you want to move a test charge QT in the presence of electric field, what is the force you need to apply? You need to apply an equal force to this in opposite direction, right? An equal force to this in opposite direction, right? So therefore the force to be applied in order to move a test charge, in order to move a test charge in the presence of electric field, in the presence of electric field, electric field should be equal to the force exerted by the electric field but in opposite direction, right? So therefore F is equal to minus QE, right? F is equal to minus QE, right? So this much force we need to apply on a test charge, right? We need to apply on a test charge in the presence of electric field, right? So therefore F is minus in the sense we are applying opposite to the electric force, right? Opposite to the electric force, opposite direction, right? So therefore F is equal to minus QE, right? And force is a vector, right? Force is a vector, right? So therefore writing force in vector form, just a minute, writing force in vector form, F bar is equal to minus QE dot AL bar, right? QE dot AL bar, right? So because let us say this is the electric field, right? So this is the electric field. We are moving a point charge, right? We are moving a point charge from one point. Let us say this is point A and this is point B, right? We are moving a point charge in the presence of electric field from one point to another point, right? From one point to another point, a distance dl, right? A distance dl, right? So therefore along the distance vector, right? Along the distance vector is AL bar, unit vector is AL bar. Along the distance vector, unit vector is AL bar, right? So therefore F bar is equal to minus QE dot AL bar, right? So let us say this is equation 3, right? So now energy, what is our aim? Energy expanded in moving a point charge. That means, in other words, how much energy we need to spend in moving a point charge, right? So energy or work done, both are same, right? So energy is equal to force into distance, right? Force into distance, right? So therefore energy E is equal to, right, energy in other words, not E, because electric field is represented as E. Let us say W, right? W is the energy, right? So this is equal to force, right? Force minus QE dot AL bar into distance DL, right? Into distance DL. So this is the differential length DL. DL is the differential length, right? Differential length in the presence of electric field DL, right? So therefore the energy is differential energy dW, right? So we are determining energy with respect to differential length DL. So therefore differential energy, in other words, differential work done, right? So therefore if you want to determine the total work done, right, total work done from point A to point B, then integrating, right, integrating, W is equal to integral minus QE dot AL bar DL, right? And here DL, capital L, is equal to DL AL bar, right? D capital L can be replaced with DL AL bar, right? So therefore and limits are from A to B, right? From point A to point B, right? In other words, from one point to another point. In other words, initial value to the final value, right? So therefore here minus Q is constant that can be taken outside. So initial value to final value E bar dot DL bar W, right? So this is the work done, right? So this is the work done in moving a point charge, right? Energy expanded or work done in moving a point charge in the presence of electric field, right? So this is the work done or energy to be spent in order to move a point charge, right? In order to move a point charge from one place to another place, right? So this is the work done, and the units are joules, right? Joules are the units, right? So this is about energy, right? And actually our topic is potential, electric potential, right? So we are discussing electric potential, right? So to know electric potential, first of all, as I said, we need to know what is energy spent or energy expended in moving a positive charge in the presence of electric field, and this is the energy, right? So this is the expression for energy spent in moving a point charge in the presence of electric field, right? And now coming to electric potential, electric potential is V, right? Volts. Electric potential is V, volts, right? Units are volts, right? So electric potential potential is the energy, right? Energy expanded per unit positive charge, per unit positive charge, right? Potential required, right? How much potential is required per per unit positive charge, right? Or in other words, same, it is the continuation for the previous one, right? It is the continuation for previous one, right? Just a minute. Right? So potential V is equal to energy, total energy per unit positive charge, right? Total energy per unit positive charge, right? So that means what? Joules per coulomb. Joules per coulomb, right? So therefore, from this equation, right? From this equation, I will take this equation here. Right? I will take this equation here. W is equal to minus Q integral initial value to final value E bar dot dl bar, right? So now, as per the definition, right? As per the definition of potential, so what is potential here? So what is potential here? Energy per unit charge, right? Total energy per unit charge is potential, right? So therefore, V is equal to W by Q, right? V is equal to W by Q, which is equal to minus integral E bar dot dl bar, right? Initial value to final value, right? So therefore, V, potential V is equal to minus integral initial value to final value E bar dot dl bar. So this is the equation, right? Potential joules per coulomb or volts So this is about electrical potential, right? And also the relationship between potential and electric field is this, right? So this is the relationship between electric field and potential. So V is the potential and E is the electric field. So this is also the relationship between electric field and potential, right? We can determine potential due to a point charge, right? So here potential due to a point charge, potential due to a point charge. So what is electric field due to a point charge? E bar is equal to Q by 4 pi epsilon naught R square AR bar, right? R square AR bar, right? So this is the electric field due to a point charge, right? So if you substitute electric field here in this expression and integrate, you'll get potential due to point charge. That's it, right? So V is equal to minus integral E is Q by 4 pi epsilon naught R square AR bar dot DL. Here DL is dr AR bar along the radial component, right? Along the radial component, right? Along the radial component, DL is dr AR bar, right? And if this is a length, right? If this is a length L, if this is a length L, then DL is equal to DL AL bar, right? DL AL bar. So whatever we represent with, right? Whatever we represent with that component we can express. DL is equal dr AR bar, right? So therefore, AR bar dot AR bar is 1, right? AR bar dot AR bar is 1, right? So therefore, and this will become, and here RA to RB, initial value to final value, right? RA to RB, let us say, right? So therefore, this will become minus Q by 4 pi epsilon naught integral RA to RB 1 by R square dr, right? So here AR bar dot AR bar is 1, right? AR bar dot AR bar is 1. So therefore, we will have this one, right? So integrating this, what will get? Minus Q by 4 pi epsilon naught and 1 by R square, right? 1 by R square integration. So what is 1 by R square integration? 1 by R square integration is minus 1 by R, right? So RA to R2. So if you substitute the limits here, if you substitute the limits here, and you will get minus 1 by RB plus 1 by RA, right? So this you will get. In other words, if you have any confusion here, writing like this, you can. So here we have minus, here we have minus, and here we have minus. So minus and minus is plus, right? So therefore, this will become plus, right? And now applying the limits, 1 by RB minus 1 by RA, right? 1 by RB minus 1 by RA, right? And here let us assume that we are moving initial point, right? From infinite, right? Initial point from infinite distance in the sense, let us say this is the electric field, right? This is the electric field, and this is infinite point, right? That means what? Where there is no electric field, right? Where there is no electric field, that is infinite point, right? So therefore, where there is no electric field, from that point we are moving a point charge, right? We are moving a point charge into the presence of electric field, right? Initially where there is no electric field, right? Initially where there is no electric field, from that point to the point where electric field exists, right? We are moving from that point. So therefore, this is the initial point, and which is infinite, right, which is infinite. So therefore RA tends to infinite. So if RA tends to infinite, then we can write Q by 4 pi epsilon naught RP, right? Since RA tends to infinite, then 1 by RA will be 0, right? So therefore, or general, in general, we can write V is equal to Q by 4 pi epsilon naught R. So this is the potential due to a point charge, right? Potential due to a point charge, right? Potential due to a point charge. And one more thing is, potential is a scalar, right? It is a scalar quantity. It is a scalar quantity. It is not a vector, right? So because there here a bar dot a bar here at this point, right? So here at this point, right? So here a bar dot a bar, right? A bar dot a bar, right, is equal to 1, right? Is equal to 1, right? So therefore there is no unit vector. That means no direction, right? No direction, right? So therefore here V is equal to Q by 4 pi epsilon R is a scalar. So therefore potential is a scalar. It is not a vector, right? Potential is a scalar, right? And similarly, you can also determine electric field due to a line charge. Potential due to a line charge or potential due to a surface charge, that you can determine, right? So simply applying, simply substituting electric field here, right? Simply substituting electric field here, here at this point. Simply substituting electric field here. So this is the electric field, right? So simply substituting here. If you substitute E bar is equal to rho L by 2 pi epsilon naught rho a rho bar, you'll get potential due to line charge. If you substitute E bar is equal to rho S by 2 epsilon naught a n bar, then you'll get potential due to surface charge, right? So this is how we can determine potential, right? So with this we have completed potential, electric potential, right? So once again let me give an overview and let me close the session, right? So here electric potential. So in order to discuss or in order to understand electric potential, first of all we need to know what is energy expended in moving a positive charge, right? So energy expanded in moving a positive charge. Energy is nothing but force into distance, right? Energy is nothing but force into distance. So therefore force, electric force. So what is electric force? Electric force is the force exerted in the presence of electric field in order to move a point charge from one point to another point, and that is nothing but minus QE, right? Minus QE, right? And distance is dl, and substituting that, and we will get the energy expanded in moving a point positive. So electric potential is nothing but energy per unit, energy spent per unit positive charge. How much energy we are spending per unit positive charge is nothing but potential, right? So therefore energy per unit charge, that means W by Q is nothing but the potential, and we have V is equal to minus integral E dot dl, right? E dot dl, that's it, that is potential. So potential due to point charge. So substituting electric field due to point charge here and integrating, and we will get potential due to a point charge, right? Potential due to a point charge. And one more thing is here, So this is nothing but the potential difference. Here you can see here. So this is nothing but the potential difference VA, right? VB minus VA, right? VB minus VA. So here this can be written like this: Q by 4 pi epsilon naught RB minus Q by 4 pi epsilon naught RA, right? So this is V is equal to, right? So this is nothing but potential at point B, and this is nothing but potential at point A, right? So this is VB minus VA is nothing but potential difference, right? Potential difference is VAB, right? VAB, right? So therefore VAB is equal to VB minus VA, potential difference, right? Potential difference, right? So therefore potential due to point charge is this: V is equal to Q by 4 pi epsilon r, and which is a scalar quantity, right? So this is about electrical potential, right? So with this I will close my session.